Good morning. Welcome to Krishna's classroom. Now we explore certain facts about the Lebesgue measure space, RK, M, script M. Okay, so let us start. Look at this. RK is a locally compact Hausdorff space which is sigma compact. Now this is the basic assumption that you have. Then we constructed a positive linear functional on CCRK a positive linear functional lambda from CCRK to R, or if you are taking complex valued functions, then of course you are making the map to R, but for non-negative real functions, the lambda of f is greater than or equal to 0. That is what we by positivity. And we constructed it in specific way such that the measure space determined by lambda on, that is RK, that means that involves determining the a sigma algebra and a measure, which is a positive measure. Okay. This is the characteristic properties of a Lebesgue measure, namely the three things, namely which I have listed here. Of course, it is complete and regular. Apart from that, it is translation invariant. That means m of e plus x equal to me, and then measure of any K-cell is equal to volume of W. Now these conditions do fix it up and allow us to call it the Lebesgue measure. Lebesgue measure is the natural measure that we build up on R in the case of R1, starting from the problems in Riemann integration. So it is from the integration theory that we have come across this, and there of course for intervals the Lebesgue measure becomes simply the length of the interval, which is the analog of that is measure of the Lebesgue measure of W is equal to volume of W for every K cell. Okay. It is translation invariant. That means if you take any measurable subset of R1, translate it to the right or to the left, okay, then you see that the resulting set has the same measure as the original one. So these are some of the important characteristics of that. So in RK, we have done this using or as a consequence of Rees representation. Now this is a landmark result, and we could avoid the difficult exercise of starting with a K cell and then proceeding with that, as in the case of Riemann integration to Lebesgue integration for R1, we didn't have to do that, and at one stroke we got this one, and then all that was left was to prove that M is a Lebesgue measure, which we have already done. That means having these particular properties. Okay, right. Now, having done that, now a few remarks about the notation. Now, we often write L1RK or to represent the functions which have the property that finite. Okay, where mod f is, of course, f is equal to now this is the notation that we use, right? And if this is finite, then you say this is the L1 space over R1. And now we shall go into the details of that and more generally to LP spaces, and then look at the structure of these spaces in due course. And of course, in R1, you recall this is the situation. Suppose I is an interval. I mean, this may be of the form AB, and B are not included. A is included, but B is not included. Or A is not included, B is included. These four types of intervals that we come across. And A equal to B, it will become a singleton point. Okay, so then you can work on this one. Integral over I fx dx. Now you see that this is the usual notation, and you see that for f belonging to CC RK with support of f contained in I. Now you see that this will become, this is integral over I f dm is the Riemann integral. Even for a larger class of functions, it is true, but at least for these class of functions, it is true. Okay. Now that's about the notation, and this standard notations that we use when we work on this. In fact, you see that if f is a Riemann integrable function and integral over I f dm coincides with what is called the Riemann integral of the function, on the interval AB, and it is written like this. Now let us, what are the some of the standard things that we should look at, or what we have gained out of this is the following, or some questions that may often come up are the following. In fact, two prominent questions we look at this stage. Now you see that this is a topological space. Rk is a topological space with the usual topology. With the usual topology. Now, consider the sigma algebra. The smallest one. Containing all open sets. This is called the collection of Borel sets. Now it is quite easy to see that all open sets are Lebesgue measurable. And hence all Borel sets are Lebesgue measurable. That means a collection of Borel sets, say Vk where Vk denotes the sigma algebra of Borel sets. Now this automatically throws one question. Is every element of script M a Borel set? One of the natural questions that come up is Vk equal to that comes up. Is is bk equal to n. This is the question that we naturally ask. So we explore this and we shall prove that the answer is no. That is, there exists a bit measurable subsets which are not Borel. We explore this. On R1. On R1. Okay. We give a cardinality here. Giving a cardinality argument. See, the strategy is that the cardinality of the sigma algebra M is greater than the cardinality of the Borel sets, the collection of Borel sets. Okay, so that's the sort of argument that we give. For that, we make the following observation. So, small c denote the cardinality of the continuum. Like say cardinality of R or the set of all subsets of set of integers. Set of integers has cardinality LF0, and one can prove that the cardinality of Pz, that means the set of all subsets of Z, also has the same cardinality as that of, so that's equal to C. So in short, we also designate this by C equal to 2 power . Now LF0 is the cardinality of the integers or even the rational numbers, but the cardinality of the real, of the set of real numbers, is in fact bigger, of course, naturally, but it is not the same as Aleph naught. Okay, so and by a construction we are justified in using this notation. So this is not exactly, there is nothing like 2 to the power Aleph naught that you can calculate, but this is only a notation, and the relation between C and Aleph naught is designated by this, and C is taken to be greater than Aleph. Now we observe that we prove this in R1, that Rk has a countable basis. Now what does the basis consist of? These are the open bars with rational radii in some countable with center at some countable dense subset of Rk. For instance, on R or R1, it is the set of all open intervals with center at rational points. I mean, that's one example. Rational points with radius rational. Where P Q, all open intervals, in fact, where P and R are rational numbers. Okay. Now this collection This collection has now the Borel sets generated by this collection this countable collection has cardinality C. It comes from a very a property of taking, because how do we get this Borel sets? Borel sets are obtained by taking countable intersections of open intervals, because it contains all open sets, all closed sets. Take the countable intersection of open sets and countable union of closed sets, and so on, and then further they are members of B, the Borel set B1. Now you see that you have many more members of this kind, and in fact you can show that the collection has cardinality C. Okay. Now on the other hand, choose R1 a Cantor set the Cantor set E with measure equal to 0. Now Cantor set is uncountable. Is uncountable. It has got cardinality C. Now this is an example of a subset of R which is uncountable, but still it has the Lebesgue measure equal to 0. Okay, it's a typical example, right? Now you can look into the proof of this result. Now you see that M is complete, measure of equal to 0, M complete implies every subset of E is measurable. With measure 0. Okay, because you know that the subsets of all measurable sets with measure 0, Lebesgue measure 0, are measurable, and that we have seen earlier. every subset of so all subsets of E are measurable. E is having cardinality C. Each one of the 2 to the power C this is actually P. That is the power set of E. S is measurable. Measure 0. We have already some information about the Borel sets. Okay, Borel sets have and E has cardinality to the power C, which is less, which is greater than. That means there are more sets Lebesgue measurable than the sets in Borel class. Okay. That is, there exists subsets one which are measurable but not Borel. Okay, because it's a larger class of subsets which are measurable than you have in R. You can actually construct them. Therefore, certainly there are some sets, some subsets of E which are not Borel sets. Okay. So that says that Borel, the collection of Borel sets does not account for the entire Lebesgue measurable sets. Account for R. Okay, so on R1 we have to, okay, on R1 itself. In general, one can develop an argument on R. Okay. So now that is one question. So we have seen that the Lebesgue measurable subsets form a larger class than the Borel sets. But the important point is all Borel sets are Lebesgue measurable. So thus all Borel sets are measurable. but there exists Lebesgue measurable sets which are not Borel. That is one question has been settled. Or in short, I think schematically we can say that this is M, and in fact we have proved it for the case k equal to 1. Okay. So Bk is properly contained in properly contained. Right. Now what is the next question? Does means is every subset of measurable. Now this question we have considered earlier. We have also given a proof of this thing. But let us recall it for completeness of this lecture. Just to put the outline the proof. So the answer is no. There exists subsets R1. In R1, not measurable. That is the theory. So this is the result. Okay. So we build a proof as follows. The theorem that we prove is the following, from which you can infer. We prove that if A contains in R1 and every subset of when measure of A equal to 0, which is a contradiction. Because you know that we are talking about an arbitrary subset of R. For instance, an interval. You know that the Lebesgue measure is not 0. But suppose every subset of A is Lebesgue measurable, then the measure of A equal to 0. Okay, right? So that is so this is not true for every subset of R1, because there are subsets of R1 whose measure is not equal to 0, right? But we have the completeness theorem. It says if measure of A equal to 0, then every subset is measurable. That's a difference. Okay? So we will get a contradiction if we prove this. Okay, so proof. From this we can infer that if you take a subset of non-zero measure, then it has a subset which is not measurable. So that is the outcome of that. So let us prove this. I will just outline the proof. We have already done this earlier when we developed a Lebesgue measure on R1. So it is just the repetition of the same. Now note that it's a group with respect to it. And the set of all rational numbers Q is a proper that's the Q is the set of rationals. Yes. Now what we do is we take up the cosets of the R1. Okay, that means sets of the form q plus some real number. Okay. Let E be the, you see, this means the following. You define an equivalence relation. Okay. Define an equivalence relation, that is x is equivalent to y if and only if x minus y belong to. Okay, that means x is equivalent to every element of the form y plus r, where r is a rational. Okay, so you can actually partition this. Now you can show that this is this is actually a partition of the whole of R. So that's the idea. So let E be the set that contains exactly one element from each of these processes. Now this exists. Such as set exists by the axiom of choice. So we use the axiom of choice to conclude that one can pick exactly one element from each one of these cosets and form a new set and call that. Okay, so we call this E, right? Now the structure of it. Let us look at the first property that you can prove is E plus R intersection equal to phi is empty if R belongs to Q and if R and S belong to Q, then their intersection is an empty set. How do you prove that? So let X belong to therefore what do you get? X is equal to y plus R, which is also equal to z plus x, where Now let us work out this. What is the consequence? The consequence is that y plus r therefore y minus z uh, equal to s minus r which belongs to q. Okay, what does this mean? See, y and z are in E. They cannot be in the same coset because there is exactly one element chosen from a coset. Okay, so they cannot be in the same coset. But what does this say? This says that y and z are in the same coset. The same coset, which is not. Because what happens is in E, there could only be one element from one coset. Exactly one element from one coset. Okay. E contains coset of. So that is one observation. The second observation is every R1 belonging to. So let y be the element same coset of x. Okay. Then what we have is x minus y equal to r. This belongs to P. What does this mean? That is x is equal to y plus. Okay. So x minus y belonging to Q implies Q plus y. Now what you do is, now use these results. Let T belong to be a rational. For any A contained in R1, we are now going for that argument. Choose an A contained in R1, put AT A intersection T plus 2. Now AT is measured. Is measurable. By hypothesis. So we arrive at a contradiction. Okay. Let K be a compact subset of let H be equal to union K plus R, where R belongs to set of all rationals on the interval 0 to 1. This is the definition of it. Now what do you get? H is bounded. Why it is bounded? Because it is K, the union of K plus R for all rational numbers R. Okay. For all rational numbers that lie between, not all rational numbers, but all rational numbers on the interval 0. Okay. Measure of x is 5. So k is contained in by A the sets k plus r disjoint. So what does this mean? This means you see that the measure of h is equal to sum of the measures of k plus r. Okay. So this means so suppose measure of k plus r is and measure of k plus r, because it is Lebesgue measure of k. So if measure of k is positive, then measure of h is positive, is infinity. But that's a contradiction. Okay. Measure of k is equal to 0 for every k which implies in turn measure of equal to 0, because you see that it's a regular measure. Okay. Therefore now a is equal to 20 countable. It follows that measure of a equal to 0. So we have proved that if you take a measurable set, then every subset of that set is measurable. Okay. If A is a measurable set, the big measurable set subset of R1, then the measure of A is equal to 0. But this is impossible. Cannot measure. So that's the proof of this theorem. Okay, or as an application of this theorem, we can get this result. So we have settled two questions, namely there exists Lebesgue measurable sets which are not necessarily Borel sets. Secondly, the Lebesgue measurable sets do not cover the entire class of subsets of R. Okay, so there are subsets which are not measurable. So I conclude this talk with this. Thank you very much.